All right, so we've talked a little bit about changing the graphs of sine and cosine. So we looked at your vertical stretching and compressing, which impacts your amplitude. We looked at the horizontal stretching and compressing, which affects the period of the graph of the function. Um, the phase shift is your horizontal shift left or right, and your vertical shift is going up or down. So just to kind of summarize our functions in the form a sine of bx minus c plus d, or a cosine of bx minus c plus d. For sine and cosine, your domains are all real numbers. You can take the sine or cosine of any angle you wish. So as we scroll further right and as we scroll further left, every value of x will be somewhere on this graph. Our outputs range in value from -1 to +1 for both sine and cosine. So our range for both functions is -1 to 1, something that we're going to have to keep in mind down the road when we look at inverse functions and switching domains and ranges. All right, so also want to talk about a concept known as simple harmonic motion. So it's a bit of an application of what we've talked about in this section. So we can model various physical phenomena such as displacement on a spring, sound waves, or waves on the electromagnetic spectrum. So here we have our, we're going to use the sine one for this. But for our function, f of t equals a times the sine of, and this weird looking lowercase w looking symbol is the lowercase Greek letter omega. Again, it's not overly important that you know the Greek alphabet, but if you want to replace the a lowercase a and the omega with the capital A and the capital B, it would be all the same anyway. So just like we talked about before, taking the absolute value of this a is going to be our amplitude. Our period is 2 pi divided by, well, we had b, but now we have omega, so it's 2 pi divided by omega. And then we also have what's known as the frequency, which is just taking the reciprocal of the period. So if we have 2 pi over b or 2 pi over omega for the period, the frequency is the reciprocal of that, and typically it's measured in hertz. So again, you can think of the period as a type of wavelength, or the length of time needed to complete one wave, while the frequency is the number of cycles or the number of waves per unit of time, usually about a second. So for instance, let's say we have, we'll get a nice one here. Let's say we just do sine of pi times x. And here the period would be 2 pi divided by pi, which is 2. So here we get one full wave starting at 0 and getting one full wave till we get out to 2. So our period is 2. The reciprocal of this would be pi over 2 pi, which is a half, which if we look at the amount of wave we get between 0 and 1, we only get half, we only get the upper half of a wave. So the period will tell you the wavelength. So in this case, we get a full wave going out from 0 to 2. The frequency is how much of a wave we get between 0 and 1, usually 1 unit of time, such as a second. If we make this 2 pi, that's more of a horizontal compression than pi. And here we get one full cycle in 1 second. So 2 pi divided by 2 pi would be 1. So our period would be 1. We get one wave, and our frequency is also 1. And the higher this number, the more of a compression we get. So your sound waves typically are very large numbers here in the hundreds, which are really difficult to see because you got quite a bit of graph compressed trying to compress against the y-axis. All right, so example 5, we have a model of sound wave produced by a saxophone player is given as v of t equals 5 sine 400 pi times t, where t is measured in seconds. So part A, we're going to find the frequency and the period of this sound wave. So it really doesn't matter what order we go in. If we want to find the period first, because that's what we're more used to doing, that's fine. But the period is going to be 2 pi divided by this 400 pi. So 2 pi divided by 400 pi. And the pi's are going to cancel out. So we're left with 2 over 400, which is 1 over 200. So this is about I think 0.005, which is a very, very short wavelength. In fact, if we even graph this, it's going to look like a big old jumbled mess. So if we try to do 400, it's going to look bad. I mean, it's really hard to tell because we really have to zoom in quite a bit here. And it's almost not even worth, not counting the values of x that we have on our x-axis. It just looks like a giant rectangle. So we'd have to really adjust the tick marks on the x-axis. Right now, each of these little ones represent 0.2, so we'd have to go much, much smaller than that. But even if we made it, instead of a 400, even a 40, that's a little bit better, but we can see quite a bit of compression here because of the large number that we're multiplying our x by. So our period would be 1 over 200. The frequency is the reciprocal of that. So our frequency, we could look at it as 400 pi divided by 2 pi, or just take the reciprocal of this value, and the reciprocal of 1 over 200 is 200. So 5 sine 400 pi times t. If we go back to the original here, it's really tough to see. Oh, this one, okay, there it goes. But we actually get between 0 and 1 inside this first block here, there is actually 200 full sine waves. So again, to fit 200 full sine waves into a space between 0 and 1, we have quite a bit of compression here. So we'd have to really adjust our values here. So let's see if I can go between 0 and 1, and let's go a step of 0.02. See if that helps. Well, in any event, it's a little bit easier to see, a little bit of space between the waves. But we have 200 of these waves in this 0 to 1 interval. All right, and that's, again, 200. If this is in seconds, this is 200 hertz. 200 hertz. All right, part B, if the saxophonist increases the volume of the sound, how does the model change? Where the volume, the overall volume, is best adjusted by looking at the amplitude. And if you think of like an amplifier, which creates the ability to amplify the volume of an instrument, for instance, the guitar, or a microphone also plugged into a speaker, that acts as an amplifier as well. So if we increase the volume of the sound, that's going to increase the amplitude. So this 5 is going to go up, so our amplitude will increase. And depending on how loud the saxophonist plays the saxophone, this value could get pretty large. All right, part C, if the saxophonist changes the note played, how will that affect the equation? So the actual note played, like a C sharp or an A flat or any of the other 12 tones, is really affected by this value here, this value of 400 pi. So this 400, forgive me if my thinking is not, my memory is not as good here, but a typical A, like a tuning fork, would have a 440 here. So this is going to be below that. So this might be a G or an F sharp or an F. I really don't know off the top of my head. That's something I could look up. But how is that going to affect the equation? Well, if you change the note, it changes the value of the omega, the 400 pi. So by changing the note and playing a different note, the 400 pi value will change. So if the note is increased in tone, like going from a natural to a sharp, this 400 is going to go up in value. If it's decreased in tone, like going from a flat or from a natural to a flat, it's this 400 is going to go down. So the volume is the amplitude. That's how that is affected. The note itself is this value in front of t, this 400 pi. So, all right, that about does it for this video. Thanks for watching. I'll